Okay, so last time we I introduced the vowel group and the root datum of algebraic group. So yeah, in this context, we're thinking about connected reductive groups. So if you have a connected reductive group, then its vowel group is the normalizer of a maximal torus mod the torus. And it's, yeah, you need to choose a maximal torus to make this definition. But since any two maximal tori are conjugate, this definition is independent of which torus you choose. It also turns out to be a finite group. And the other remark here is that for a general algebraic group, the vowel group is normalizer mod centralizer for maximal torus. But for reductive groups, the centralizer of a torus is the torus itself. So that's a vowel group. So it seems maybe a bit unmotivated to define it in this way, but it turns out to relate to many things. So, so we had the example that the vowel group of GLN is the symmetric group. I guess I didn't prove this super rigorously, but it's true. I gave you at least one direction. So the place where the most prominent place where the vowel group comes into play is by its action on the characters of the torus. So there's because the vowel group is defined as a normalizer, the torus mod the torus, it acts on the characters, and therefore it acts on anything we build out of the characters. So for example, we can look at the real vector space generated by the characters, and W will act on that. So yeah, there was this technical point. So the way we connect things to root systems is we can consider the adjoint action of the torus on the Lie algebra. And since the torus is a diagonalizable group, we can split up the adjoint representation into the isotypic components for the various characters of the torus. So G will be the direct sum of these G chi's, and the roots of G with respect to T, we still need to choose a torus T, but everything will be isomorphic if we choose a different torus. The roots are the characters that appear, the non-zero characters that appear in the adjoint action. Yeah, we think about their span inside this real vector space. And the big result from last time, or one big result from last time, was that these form a root system. And the isomorphism class of this root system does not depend on the choice of maximal torus. And the reflection group associated to this root system, so generated by all the reflections across the roots, is exactly the vowel group of G. So I didn't really prove this theorem, but I gave some indications of how things work. And some examples. So for SL2, we just got the root system consisting of 2 vectors. And for PSL2, we got the same thing. So those for the SL2 case, those 2 vectors were naturally identified, most naturally identified with 2 and -2. For PSL2, they were the root system is just 1 and plus or minus 1 over here, 1 and -1. And for GLN, we can, yeah, I described the GLN case. We get the A n -1 root system. Okay, so, and then, yeah, some ingredients of the proof of the theorem. It comes down to thinking about semi-simple Lie algebras. And I gave this reference to Fulton and Harris, where they have a nice discussion of how these things work for semi-simple Lie algebras. And the connection to the vowel group is through the centralizers of the kernels of the roots. So these are certain connected reductive subgroups. I think I have that here somewhere. Yeah, each of these is connected reductive subgroup. They generate G. Their commutator is isomorphic to SO2 or PSO2. And then thinking about each of these G alphas individually, you can prove that kind of the vowel group for each of the G alphas is just Z mod 2Z, and each of those contribute a reflection to the vowel group of G. And from there, I didn't really spell it out too much, but that's kind of the idea. Okay, and so that theorem that we saw gives us a way to associate a root system to any reductive algebraic group. And I mentioned the classification of root systems last time. And so we can split up reductive groups into families based on their root system. So there's the AN family with SLN or SLN plus 1 and GLN plus 1, as well as PSLN plus 1. There's the BN family, CN family, DN family. And then there's the exceptional groups. So we had that. So the root system tells us which member of a family a given reductive group is, but it doesn't distinguish different reductive groups within the same family. And so in order to get a more refined invariant that lets us distinguish different reductive groups, we need to use the root datum. So the root datum is a certain quadruple where X and X check are free abelian groups that are in a duality pairing. And R check are finite subsets that are in bijection and satisfy a certain property. That are in bijection. And then the axioms are the following. So a given root and the corresponding co-root paired to 2, and then R and R check are stable under the reflections. And so what happens is that R is a root system inside of a real vector space, given by it's a root system inside of its span inside the real vector space corresponding to X, and similarly for R check. That's what this second remark is saying here. And so some examples. So we saw the SL. I gave you this abstract example. It'll turn out to correspond to SL2, and this other abstract example will correspond to PSL2. And then there's this one that will correspond to GL2. So the root datum of a reductive group, to define it, we take X to be the character lattice, X check to be the co-character lattice, and we already have the roots. So that's R, and and R check. Well, so we need to do something to check that R check lives inside of the co-characters as opposed to just in this vector space spanned by them, but that's true. And so that lets us define the root datum of an algebraic group in the following way. It's kind of good. So root datum is the singular, root data is the plural. I think I should have written root data here, but anyway. And so that's the root datum of an algebraic group is a complete isomorphism invariant. And moreover, every root datum defines a unique reductive group. So so this is the classification theorem for reductive groups. They're completely determined by their root datum. And I made this final point that if you take the root datum you just take a root datum and you switch the two factors, then you get a new root datum and the corresponding reductive group, and by the theorem it must correspond to some reductive group, and that group is called the Langlands dual group of the original group. So the original reductive group that corresponds to our original root datum. And I just said, without too much explanation, I guess without too much explanation, I said that that Langland's duality switches adjoint and simply connected. So in particular, SLN and PSLN get switched under Langland's duality. We saw that for n equals 2 in the concrete examples. And GLN is sent to itself under Langland's duality. We saw that for the n equals 2 case. And usually the Langland's dual is of the same type, except for Bn and Cn where they get switched. Okay, and then I had an appendix with some things that you could read if you're interested, but I don't think I want to spend too much time on those things unless there are specific questions. Yeah, so that was the material from last time. Any questions on this stuff? Okay, great. So then let me switch to the new material. Yeah, so in this last lecture, I want to kind of give a bit of a summary of some things we've covered and some further directions that you can explore in later classes or in your own studies. So again, I won't prove too many things. This is meant more as an overview. Also, I won't really the material that I'll present today won't be necessary for any of the final exam problems, but it will motivate a few of the problems. So I don't know if it would necessarily, yeah, you're not super responsible for this material, but it may help to give some context to some of the problems and some motivation. Okay, but if you just want to like enjoy and not worry about the details too much, that's fine too. Okay, so the first thing I want to say is about the structure of reductive groups. I want to go back to a point that I made in the very first lecture. So let G be a reductive group. Then we saw that we can choose a maximal torus inside of G. And we can also choose a Borel subgroup of G that contains this maximal torus. So T is contained in B and B is contained in G. One thing to note is that there's always an opposite Borel subgroup that intersects the original Borel subgroup only in the torus. So they share T as a maximal torus, but they don't share anything else. There's several ways to think about this opposite Borel subgroup. One kind of the most intrinsic way, I guess, would be to think about it as a certain conjugate of B, and it's the conjugate by a lift of the longest element in the vowel group. So the vowel group has a notion of length. There's a length function on it, which I'm not defining, but there's a unique longest element, and you can conjugate B by it, and you get B minus. Another less intrinsic way to think about it is you can embed. So first of all, for GLN, if you take the Borel of upper triangular matrices, then the opposite Borel will be lower triangular matrices, and they intersect in diagonal matrices. And if you have a general group, you can embed it into GLN. You can arrange so that the Borel is in the upper triangular matrices, and then whatever maps to lower triangular matrices will be the opposite Borel. So that's another way to think about this opposite Borel. So just upper triangular matrices versus lower triangular matrices. And okay, so then we also had the root system, which, as I just said, is all the characters of this torus that appear in the adjoint action, the non-zero characters that appear in the adjoint action. And the Borel actually defines a set of positive roots. So I mentioned how you can, if you have the root system, you can just pick a hyperplane, generic hyperplane, and just say that the things on one side of the hyperplane will be positive roots. So it turns out that another way to choose a set of positive roots is just choose a Borel containing the torus. And then the adjoint characters that appear the characters that appear in the adjoint action on the Lie algebra of that Borel subgroup will form a set of positive roots. So picking a Borel that contains T and picking a set of positive roots is essentially the same thing. And in fact, the roots that the set of negative roots, so the roots that appear inside the adjoint action on the opposite Borel will exactly be the negatives of the roots that appear in the adjoint action of the original Borel. So that's on the other side of the hyperplane if you're thinking about this geometric picture. Okay, and anytime we have a set of positive roots, we can choose the simple roots. So these are ones that cannot be written as a sum of other positive roots. And then, so if we choose those, then their negatives will be simple roots for the set of so-called positive roots that are on the other side of the hyperplane. So now I wanted to go back to this picture that we had in the first lecture, because now it should make some more sense. So so this is kind of inspired by Grothendieck, and the picture itself is from Milne's book, so you can take a look. It's near the beginning, I guess, in the introduction. You can take a look there. So the idea is that, so this is supposed to be a picture of a reductive group. So the body here of the butterfly is a maximal torus, and the wings are opposite Borels. So this is one Borel, this is another Borel. You can kind of see the B here, and these pins here are the roots. So they rigidify this structure, and you have the roots for the Borel and the roots for the opposite Borel. So that's, I just wanted to explain that picture again now that we have all the terminology. Okay, so yeah, any questions on that? Okay, so the next topic I want to touch on is Tannakian reconstruction. So this is a section in chapter 2 of Springer that we skipped. But now I want to go back to it. So so in this section, G will be just a general linear algebraic group. I know we've been talking mostly about reductive and semi-simple algebraic groups, but in this section, it's just any linear algebraic groups. We will reintroduce the reductive assumption later on, but for now, G is just general. And rep G will be the category of all finite dimensional representations of G over our algebraically closed base field K. So yeah, so I think most of you are familiar with basic category theory. The objects here are the finite dimensional representations of G, and the morphisms are G linear maps. And so the idea of Tannakian reconstruction is that you can recover the group G from its category of finite dimensional representations, and you can recover it as a group and as an algebraic variety. So you can recover both structures. So another way to think about this is that this procedure of Tannakian reconstruction characterizes which categories appear as representations of groups. So if you have a category that satisfies certain properties, then you'll know that it's the representations of an algebraic group, even if that wasn't how it was given to you. So maybe it's given to you by some geometric procedure or some combinatorial procedure, but if you know that it satisfies certain properties, then you know that it's the representations of a group, of an algebraic group. Linear algebraic group, in fact. Okay, so that's the idea. So how does it work? We need a bit of setup. So let's say we have a finite dimensional representation of G. Rho V is the map. V is the vector space. So first of all, the dual vector space of V also has a structure of a representation of G. So just some notation, these brackets will be the evaluation map, evaluation pairing from V dual tensor V to K. And then the the dual V dual have an action of G given in the following way. So little g acts, it takes the dual, takes an element of the dual, so this is a linear functional on V, to a new linear functional that takes a vector in V to the things that we get when we first translate V by G inverse and then evaluate that translate at V dual. And by this dot here, I mean rho V of G inverse applied to V. So the nice thing about defining it in this way is that this evaluation map becomes a G invariant map. So if you translate both V and V dual, a linear functional, then by G, then you get the same thing when you evaluate as if you had just evaluated to start with. Okay, so I think this is a procedure we did maybe even multiple times during the course, but I wanted to highlight it again. So there's any representation. So anytime we know that a representation lives in rep G, its dual also lives in rep G in this way. Another thing we need as part of the setup is that if we have another representation of G, let's call it W, then the tensor product V tensor W of these two vector spaces also carries the structure of a representation of G. So how does this work? Well, if you have a little g, how does it act on the tensor product? Well, it takes this simple tensor little v tensor little w to another simple tensor, which is produced by taking acting on g acts on v and g acts on w. And again, this acting here is rho sub capital V. This is rho sub capital W, this map here. So and then this extends in the obvious way to non-simple tensors. All right, so in other words, rho V tensor W is just the tensor product of rho V and rho W. Okay, so that means that anytime we have two representations of G, you can think of them as two objects in this category, we can make a new object, which is its tensor product, the tensor product of these two objects. So for those of you interested in category theory, what this means is that rep G is a rigid tensor category. So tensor means that we can always form the tensor, there's a tensor product construction in the category. It's also called monoidal category, monoidal structure, and rigid means that everything has a dual in a certain sense. But don't worry about the terminology if you're not so familiar with it. I just wanted to point it out to those of you who've heard about these things before. Okay, so that's kind of the setup. So let me state the theorem. So let's suppose, so it takes a little bit, it's a bit of a mouthful, but let's go through it. So let's suppose that for every object in this category, for every finite dimensional representation of G, we're given an automorphism of V as a vector space. Let's call it alpha V. So we have for every representation an element in G of V. And moreover, we suppose that these alpha V's satisfy the following three conditions. So first of all, if we take the tensor product of two of them, alpha V and alpha W, then we get something that lives in that lives in Geo V tensor W, and we want it to be exactly alpha V tensor W, because we know this is a representation of G, so it must have its own alpha, and that alpha is just given by the tensor product of these two alphas. And the second condition is that if we have a G linear map from V to W, then we want to know that that it commutes, that if we do alpha, so there's a commutative diagram here. Maybe it would have been clear if I wrote the commutative diagram. But if we did phi, and then we did alpha W, that's the same as doing first alpha V and then phi. So phi takes the the alpha v to alpha w. It's compatible with these alphas. And notice that this equality lives in just Halm v to w. It's not necessarily G linear, because these alphas are not necessarily G linear. Okay, and final condition is if we have the trivial representation, then so if we have the trivial representation, then then it's one-dimensional, so its GL is just the multiplicative group, and we want this alpha to be equal to 1 there. Okay, so those are all the conditions these alphas need to satisfy, and if we know that these alphas... Oh yeah, go ahead.
I have a question about A just. Is it always the case that if you take two automorphisms, if you take the tensor products of them, you will get it an automorphism? Is it always the case, or this is part of the condition?
Sorry, I didn't hear the question. Could you say it again?
Yes, if you take for general automorphisms of V and W, and you take the tensor product, will it be an automorphism?
Yeah.
Tensor W? Okay.
Yeah. Yeah, so it's not, the condition is just that, yeah, this happens to be living in GO V tensor W, but it's not, yeah, okay. So, okay, so those are the conditions, and if we have these alphas that satisfy these conditions, then the theorem asserts that there's a unique element in the group such that this alpha v is actually rho v of G for any representation of the group. So we already know. Okay, so maybe one way to state this. So I'll give several different interpretations of this, but one way to state this is that if you do have an element of the group, then you can just look at its action on all the v's. And that gives you a set of alphas, and those alphas satisfy these properties. And then the theorem says that if you happen to have alphas that satisfy these properties, then it must have been coming from the group. So it must have been a rho G. Alpha v must be rho Vg for some element of the group, and that element does not change as you go from representation to representation. So I hope that makes some sense. I'll give another way to state this result in a minute. So just a few comments about the proof. So the way you prove it is that you can look at, so first of all, you can look at the proof in Springer. It's not too bad, but let me just hit some of the key points. So first of all, you'll recall this fact that the affine algebra of G is a union of finite dimensional G representations. That's something we proved. Maybe it was a homework exercise. And so because of that, there's a well-defined element in GO of the affine algebra. So this is an infinite dimensional space, but we can still think about automorphisms of it as a vector space, and we can define a well-defined element alpha sub k brackets G inside here using those finite dimensional pieces. Okay, so this gives us a linear map. In fact, it has to be a invertible linear map from the affine algebra to itself. And the next step is to argue that this is in fact an algebra automorphism, so it respects the algebra structures. And that comes from just using some of these properties of the alphas, I guess, especially A and B. Okay, so that's an algebra automorphism. And because it's an algebra automorphism, there's an associated isomorphism of varieties from G to G. And then you just take, so this isomorphism will not be a group homomorphism. It's just some isomorphism, automorphism of G as a variety. And you can just take this little g to be the image of the identity element under this automorphism. and then that'll satisfy all the properties. So yeah, so that's the idea of the proof, and yeah, so let me give an aside, which is the categorical interpretation of this result. So again, you can ignore this stuff if you're not so familiar with category theory, but I for completeness, I wanna explain this other viewpoint on this theorem. Okay, so there's a forgetful functor on rep G to K vector spaces. So anytime we have a representation of G, it's in particular a vector space. So we can just forget the representation structure and just remember the vector space structure. So there's a forgetful functor. And what we do is first thing to observe is that any element in the group defines a natural isomorphism from the functor to itself. So in category theory class, you learned about functors, and there's maps between functors, which are called natural transformations. And if a natural transformation is invertible in the appropriate sense, then it's called a natural isomorphism. So any little g defines a natural isomorphism from this functor to itself. What does that mean to be a natural isomorphism or just a natural transformation? That means that for every object in the source category, so rep G, we have a linear map. We have a morphism from the target to itself. In this, because we just have one functor f here. And what this does in this particular case is, so for V, if we take V, then we need to give a map inside this category vec from f of V to f of V. So f of V, but f of V is just V as a vector space. We forget the representation theory structure, so we just need to give a linear map from V to itself. That's it. And what linear map do we give? Well, we have our little g. We do the action of little g on this representation V. And so you can check that this is a natural isomorphism from this functor to itself. And another thing that happens is that so first of all, there's a compatibility with the group structure. So if we had eta G and eta H, then we can compose those two natural transformations, and what we get is exactly eta GH. So there's this compatibility. And the other thing to check is that this construction respects the tensor structure. So that's pretty clear, because the tensor product of two representations has underlying vector space, which is the tensor product of the underlying vector spaces. So anyway, when you spell out what needs to happen, you verify that everything's fine, and what you get is is a map of groups from G to the tensor automorphisms of this forgetful functor f. And the Tanaka theorem proves that this map is an isomorphism. So the group is given as the tensor automorphisms of this forgetful functor. So that's the categorical interpretation of this theorem. Just so one more note about this is that that recovers the group as a group. Maybe you're wondering about the algebraic structure. Well, you can also recover the affine algebra from the category. So it'll be a certain quotient of the following space. So you run through all the representations of G, and for each you take V dual tensor V. And then you can, so this is just some vector space, you can define a quotient of this, which will be a certain algebra that may have nilpotents. And then if you quotient out by the set of nilpotent elements, by the ideal of nilpotent elements, you recover the affine algebra of G. So you can look at these sections in Springer. It's pretty concrete. If if you have any questions or it's not clear, let me know. And also chapter 9 of Mill covers this stuff too. It gives a nice perspective. So yeah, so I want to mention something about an application of this Tanaka theorem, but first I'll pause and ask for any questions. Okay, so yeah, so once again, this Tanaka theorem, it says that yeah, it says that we can recover a group from its category of representations, and actually more generally, it says the more general statement of this result is something like if you have a category with a forgetful functor, so a faithful exact functor that also respects the tensor structure, and then the tensor automorphisms of this functor form a group, and the original category is the representations of that group. Okay, so so one application of this idea is the following. So let's consider the semi-simple case. So G is a semi-simple linear algebraic group, and we have its Lie algebra G, frac G. Then we have the category of finite dimensional representations of the Lie algebra. And I mentioned this result before, that that there's a relationship between the category of finite dimensional representations of the group and finite dimensional representations of the Lie algebra. So let me state it again. So there's a fully faithful functor from rep G to rep frac G, and if G is simply connected, then this functor is an equivalence of categories. So fully faithful means that that it's an isomorphism on the Hom spaces. So if you have two representations of G, any homomorphism, G linear homomorphism between them will also be a Lie algebra homomorphism, and vice versa. Right. So let me kind of give the idea of the proof. So first of all, what's the functor? So it's given by differentiation. So if you have a representation of G, how do we get a representation of the Lie algebra? Well, we saw this already. So if we have a representation of G, then we can differentiate at identity. And so the differential of this action map will be a map from the Lie algebra, which is the tangent space at the identity of the group, to the Lie algebra GLV, which is the tangent space at the identity of the group GLV, and it'll be a map of Lie algebras, and it gives V the structure of a representation of the Lie algebra of G. So that's the functor. So we already know what it is, and so to the next step in this proof is to check that the category of representations of the Lie algebra is a rigid tensor category. So there's duals and there are tensor products, and everything's compatible. And there's a forgetful functor to vector spaces, and yeah, this functor is faithful and exact, and it's compatible with the tensor structure. And so then you think about tensor automorphisms of this forgetful functor, and so that's a group, and rep G will be the category of rep frac G will be the category of representations of this group, and one needs to show, so that there's some work here to show that this group is actually semi-simple and simply connected. So we call it G tota. So we have an equivalence of categories between the representations of the group G tota and the representations of the Lie algebra G. So there's a lot here in this step, but that's where this Tannakian reconstruction is applied. And then final step is to show that actually you can define a covering map, finite covering map from G tota to G. So G tota is the universal cover of G. So yeah. So that's that. I think that's all I want to say about Tannakian reconstruction for now. Are there any questions? All right. So next topic I wanna talk about is the Chevalley restriction theorem. So again, we're in the semi-simple setting here, and let's let A rep. So this will be my notation: A rep frac G. This will denote the set of isomorphism classes of irreducible representations of the Lie algebra of our group. And so the motivating question for this discussion is there a way to parameterize the irreducible representations of this Lie algebra? And we'd be especially interested in parameterizations that use some sort of geometric or combinatorial data. I mean, there's various ways to do this, but I'll kind of present one approach. And this is the motivating question. So as a first step, we make some observations. So first of all, we in the lecture about Lie algebras, I introduced the universal enveloping algebra, and I also I think I stated this result that representations of the Lie algebra G as a Lie algebra are the same as representations of the universal enveloping algebra as an associative algebra. So the universal enveloping algebra is an associative algebra, just like you learned in the first semester algebra course. And we can think about modules for this algebra. And so it's modules. So I'm going to use representations and modules interchangeably. So its category of modules is the same as the category of representations for the Lie algebra. So that's the first observation, that it's enough just to consider this algebraic, this algebra object as opposed to the Lie algebra. And there are various advantages of doing this, and one of them is explained in the second statement, second observation. So if you have any non-commutative algebra, then and you have some irreducible representation of A. So in other words, a simple A module. So A acts on this vector space. I guess I want it to be finite dimensional. Yeah, I should have said that, sorry. But V is finite dimensional. So if you just have a finite dimensional A module that's simple, then by Schur's lemma, the center of A acts by scalars on V. You probably saw Schur's lemma in the context of group representations. That if you have a finite group representation theory. So if you have a representation of a finite group, then the center acts by scalars. The same idea extends to show that if you have a finite dimensional simple A module, the center of A acts by scalars on V. So what this means is that there's for a fixed simple module V, there's a map from the center to K, such that the action of anything in the center, so Z is in the center, on V is just scalar multiplication of V by the scalar chi sub V of Z. So we think of this as a character of the center. So we were talking about characters in the context of algebraic groups, and there we map to GM. But here we just think of characters of algebras, which are just one-dimensional, basically one-dimensional representations, so just maps to the ground field. So chi V is called the central character of this representation V. So that's basically Schur's lemma. And that's the first part of this observation. I guess there's more to it. Let's kind of abstract this away a little bit and say that we have a map from the set of irreducible representations of A, the set of simple A modules, to the set of algebra homomorphisms from the center to K. And this just takes V to this central character chi V. So to any simple A module, we have this algebra homomorphism from the center to K, this central character. That's why this is called the central character map. Okay, so now in many situations, this center, which is a commutative algebra, turns out to be the affine algebra of an algebraic variety X. So let's suppose we have some crazy non-commutative algebra A, but its center happens to be the affine algebra of a affine algebraic variety X. Then this, what the central character does, it maps to algebra homomorphisms from that affine algebra to K, but those are just the maximal ideals of the affine algebra, which are the points in X. So in that way, to any simple A module, we can associate a point in X. So here, this is the connection with geometry, because now we can start with something algebraic and associate a point in a geometric space to it. And in many cases, so yeah, this is incredibly powerful. In many cases, this will have finite fibers. So basically, we just need to consider the geometry of X and finite other data about the representations of A. Yeah. As a side note, this also relates to Azumaya algebras, which is something I'm quite interested in, but it's not really so relevant to this course. Okay, so we have this construction. So based on these observations, in order to parametrize, so let's go back to the original question. The original question was to parametrize the irreducible representations of the Lie algebra. And based on these observations, we see that this one way to parametrize these is to understand the center of the universal enveloping algebra. So the irreducible representations of G are the same as the irreducible representations of the universal enveloping algebra, and then we can use the center of the universal enveloping algebra to give us some sort of parametrization of those simple modules up to it'll turn out to be enough. So a priori, maybe there's some more things we need to consider in these fibers, but it'll turn out that there's nothing else to consider. Okay, so that's kind of the idea behind the Chevalley restriction theorem. Now let me set up some things to actually state the result. So as usual, we fix a maximal torus, and we have its Lie algebra. So the Lie algebra of the maximal torus is just an abelian Lie algebra. The bracket is 0. So it's really just a vector space, but we have it. And we have the dual T star. And I want to recall a few things. So first of all, so this was, I don't remember if I assigned this as an exercise, but this was an exercise in chapter 4 that there's a relationship between the characters and co-characters of the torus and its Lie algebra. So specifically, the Lie algebra of the torus is the tensor product of the co-characters with our field over the integers. So if we extend scalars from the integers to K on the co-characters, we recover the Lie algebra of T. So this works nicely because there's no bracket and the tori are determined by their characters, so it works out. And on the dual side, if we take the characters of T and extend scalars to K, then we get a canonical isomorphism with the dual of the Lie algebra. So these isomorphisms are canonical. So you can go back to I think this is a discussion with examples, and these are some exercises. You can go back and check these things. So that's one thing I wanted to recall. The other thing to recall is the vowel group and its action on the characters. So I guess I just mentioned that when I went through the last week's lecture, but we have the vowel group and it acts on the characters. And as a consequence, it acts on the the dual of the Lie algebra, because that's just the extension of scalars here. And since this is an affine algebraic variety, it acts on the affine algebra of the dual of the Lie algebra. Okay, so I think this is a good place to take a 5-minute break. So yeah, so let's take a break and resume in 5 minutes. I'll ask for questions as soon as we resume. Okay, so I just set up some of the things we need to state the Chevalley restriction theorem. Any questions on the setup? Okay, yeah. So we had the Val group acting on the dual of the algebra of the torus, and also on the affine algebra of the dual of the Lie algebra of the torus. Okay, so the Chevalley restriction theorem, or one version of it anyway, says the following. So first of all, there's an isomorphism of algebras. So the center of the universal enveloping algebra is isomorphic to the W invariant functions on the dual of the Lie algebra of the torus. So this algebra here, this affine algebra, has a W action, and if we look at the things that are invariant, so this is like an infinite dimensional W representation, and if you think of if you consider the invariant vectors, that's a subalgebra, and that subalgebra is precisely the center of the universal enveloping algebra. There's an isomorphism with the center of the universal enveloping algebra. So that's what this theorem, the first part of this theorem, says. Another thing is that this, if we think about what if this algebra and the invariants, it turns out that this is the affine algebra of a different variety, and that's exactly it's the affine algebra of the orbit space. So we have the W orbits on the dual of the Lie algebra of T, and the orbit space is itself an affine algebraic variety, and the affine algebra of that orbit space is exactly the invariant. So that's something kind of special that happens when we have these reflection groups acting in a nice way on these vector spaces. Right, so I'll say something more about this in the remarks below. And the third part is that this central character map is injective. So any representation, irreducible representation of the Lie algebra is determined by the action of the center of the universal enveloping algebra. So we take a representation of the Lie algebra, we think of it as a representation of the universal enveloping algebra, we check to see how the center acts, and that gives us a central character, which by these previous two parts is a point in this algebraic variety, and that completely determines the representation. It's not surjective because, yeah, so we're only considering finite dimensional representations, so it's only injective, and the image is discrete. Yeah, I'll make some remarks about that below. Okay, so that's the statement. So some remarks about the statement. So first of all, how do you think about this first part, this isomorphism? Well, the center. So one way to think about this is one thing to consider is that maybe you learned about group algebras of finite groups, and there the center of the group algebra is functions on conjugacy classes of the group. So in a similar way, here the center of the universal enveloping algebra has to do with conjugacy classes in the Lie algebra. And so let's just think about the GLN case. So in GLN, conjugacy classes are described by Jordan normal forms, as we talked about. And these Jordan matrices are almost diagonal matrices. You have some things on the first off diagonal, but they're almost diagonal matrices. So that's why the torus appears here. So the torus is about diagonal matrices. And to explain this vowel group action, so in the case of GLN, the vowel group is a symmetric group, and the fact that we take invariance for the vowel group is corresponds to the fact that the Jordan blocks, when we do the Jordan decomposition of a matrix, the Jordan blocks are only well defined up to permutation, so we can permute them. We can permute the order in which they appear, and we stay within the same conjugacy class. So that's some kind of vague motivation for why you might expect something like this to be true. Okay, and for the second part, it turns out that it's not only is this quotient an affine variety, but it's just a vector space of the same dimension as T star. Yeah, that's yeah. So the invariance, if you look at the affine algebra of T star is just a polynomial algebra. And if you look at the invariance, it turns out to be again a polynomial algebra. So it's pretty, the proof is pretty straightforward for the symmetric group, just acting by its permutation representation. So then for the third part, the thing to say is that, so as I said before, the image is discrete inside of this is just a vector space, and it can be described as somewhat combinatorially and explicitly in terms of dominant weights. So basically you take a fundamental domain for this W action, and then you think about which elements, which points in that fundamental domain appear as the central characters of irreducible representations, and that forms this cone, the discrete cone. So there'll be, it's kind of like a lattice that you intersect with a cone, and you get this discrete cone inside of T star, and those are the dominant weights, and that's a way to understand, to parameterize the irreducible representations. So I decided not to go into all the detail with definitions and stuff because it gets pretty messy pretty quickly, but there'll be some examples about the SL2 case on the take-home part of the final exam. So hopefully you'll get at least a vague sense of what's going on. So speaking of SL2, let's kind of try to figure out what this theorem is saying in the case of SL2. So as usual, we have the maximal torus of diagonal matrices. Before talking about the universal enveloping algebra, let me talk about something easier, which is the vowel group. So as we pointed out before, the vowel group is just Z mod 2Z, and it acts on it. So its action on characters is just by negation. So the non-trivial element acts by negation. So then on this vector space T star, it'll act again by negation, by multiplication by -1. And so so what are the invariants? Well, the affine algebra, as I said before, is just a polynomial algebra. In this case, we're in rank 1. So it's a polynomial algebra in one variable x. And the vowel group acts by sending x to -x. So the invariant things are the polynomials in x squared. So those are the W invariants in this case. So it's very, very explicit. And the universal enveloping algebra, I mentioned these relations before. Maybe it's not super, maybe you didn't get a chance to really digest this. That's okay. I hope I can still communicate some of these results to you. So it's the free algebra generated by 3 elements. So because SL2 as a Lie algebra is 3-dimensional, we have 3 generators here, and the relations are given by the relations in SL2, except we don't. There we had the commutator in the Lie algebra. Here we have this commutator in this free associative algebra generated by these things, but the relations are in some sense the same. And inside the universal enveloping algebra, we have this element, the Casimir operator. So in the lecture about semi-simple and reductive groups, I mentioned there was this result that any representation of a semi-simple group is completely reducible, so it's semi-simple as a representation. And in that proof, I mentioned very briefly this Casimir operator here. So that's making a reappearance. As you can tell, it's a pretty important thing to consider when considering representations of the Lie algebra. But anyway, this is an element of the universal enveloping algebra. It's not in the Lie algebra. It's only in the universal enveloping algebra. And you can go through these relations and check that it's central. By contrast, the Lie algebra doesn't have any center. The Lie algebra of SL2 doesn't have any center. But the universal enveloping algebra does. And this is in the center. And the Chevalley isomorphism goes from polynomials in x squared to the center, and it takes this generator x squared to this Casimir operator, and it's an isomorphism. So anything in the center is just a polynomial in this Casimir operator. And it's also not a coincidence that here we had x squared, which is like a quadratic thing, and here this Casimir operator is a quadratic thing. Yeah, so that's how things work in the case of SL2. There will be something more about this in the take-home exam, but it's going to be straightforward. You don't need to know anything about universal enveloping algebras. Okay, so that's that. Any questions on the Chevalley restriction theorem or the SL2 example or anything else we've talked about today? Okay, hopefully I haven't lost everybody. So now switching gears a little bit. So another topic I want to discuss is the flag variety. So again, this is moving a bit towards the sort of geometric representation theory direction. So again, G is a semi-simple algebraic group. B is a Borel subgroup of G. And you'll recall the flag variety, G mod B, which is a projective variety. So we talked about extensively the case of SL2 and more generally GLN. The flag variety in those cases parametrizes certain subspaces of vector spaces. So the flag variety for GLN is the set of all complete flags. So the data of a one-dimensional subspace, a two-dimensional subspace containing that one-dimensional subspace, a three-dimensional subspace containing the two-dimensional subspace, and so on. And yeah, it's a projective variety. And so we also choose a maximal torus of G that's contained in B. And now, okay, and there's also a quotient map from B to T. So if I mentioned this result that if we have a solvable group, then it's the product of its semi-simple part and its unipotent part, and the unipotent part is normal. Well, it's a product as an algebraic variety, not as a group, but the unipotent part is normal, so we can mod out by it, and we get the semi-simple part, which is a maximal torus. So really, it's not the same T, but it's torus isomorphic to T. So for the sake of simplicity, I'm thinking of it as the same torus T. And then yeah, for GLN, this is a map that just takes a upper triangular matrix and maps it to the diagonal matrix whose entries are the same as those of the upper triangular matrix. So this is a map of groups. If you do this for a general matrix that's not upper triangular, this is not a map of groups. But for upper triangular matrices, this works out. So we have this projection map. Okay, so now I want to describe a procedure that takes a character of the torus and produces a line bundle on the flag variety. So let's see how this works. So let's take a character of the torus. So this is just an algebra homomorphism from T to GM. And now let's pull it back to a character of the Borel subgroup. So we have character of T here, we pull it back, we get a character of B. That's all that's happening there. And just a bit of notation. So this, I'm going to call K lambda the resulting one-dimensional representation of B. So B acts on this K lambda via this character lambda. So yeah, so that's it. That's just notation. Okay, so here's the construction. So let's take a character of the torus, and I'll define the space curly L sub lambda, which is the following. So we take G cross K. So we just cross it with this one-dimensional vector space. You can think of this as the trivial line bundle on G. And we mod out by the following relation. So if we had an element of the group that's of the form G times B, and we have it's paired with some Z, then this is, we declare that this is equivalent to moving B to the other side at the cost of an inverse. So actually now I'm thinking maybe there's no inverse, but anyway, maybe there's no inverse, but we move B over and it acts by Z via this one-dimensional, via this character lambda of B on this one-dimensional space. Okay, and so then this is one choice of notation for this quotient. So B acts on G just by right multiplication, B acts on K lambda, and we identify those two actions, and that's how we get this quotient. And so,
product?
Sorry?
Is it semi-product or something?
No, so you might be confused by the fiber product. So this sort of notation is also used for fiber products, but that's different.
No, I mean semi-product of
semi-direct product?
Semi-direct product, yes.
No, it's not the semi-direct product.
Okay, thank
you. Okay, so all right, so what this L lambda looks kind of bizarre. Why do we care about it? Well, first of all, there's an action of G on it just by left multiplication. So this B here was acting by right multiplication, but then we have the left multiplication action of G on itself. And we also have this map to G mod B. So I was saying here how G cross K is just the trivial line bundle on G, because we project onto the G coordinate. The fibers are just one-dimensional vector spaces. Now, if we do this modding out, do this identification, and then we project onto G, well, we can't project onto G anymore because we have this B action. What we can do is project onto G mod B, and then the fibers will be line bundle, will be one-dimensional vector spaces. Yeah, so that's pretty easy to check that the fiber over any coset is one-dimensional vector space. And this map is equivariant for the G actions. That's kind of clear. And so this is a G equivariant line bundle on the flag variety.
What you defined now is the induction sheaf, right?
Yeah, exactly.
Okay.
Yeah, this is induction procedure. Yeah, parabolic induction for the Borel subgroup. So yeah, so we have this L lambda, and okay, so what's the connection to representation theory? Well, because this L lambda is a G equivariant line bundle, yeah, in particular G equivariant sheaf, its global sections form a representation of G. So that's kind of clear. But what's more special is that it's actually an irreducible representation of the group G, and moreover, every irreducible representation of G appears in this way. So appears as the global sections of a line bundle on the flag variety. And one thing to note is that we talked about central characters just a minute ago. You might be wondering how this L lambda, if lambda is the character, central character of this representation, that's not the case. You need to do this business with shifted W actions, but there is an explicit relation, but it's not lambda on the nose. Yeah, and yeah, okay, so that's a special case of the Borel-Bott theorem. So the example of SL2, SL2 is the following. So there, the flag variety is just P1, and the action of G is by Mobius transformation. So SL2 acting on P1, and for any, so the character loss in this case is just integers. So for any integer, we get a line bundle on P1. And so maybe you know about the Serre twisting sheaf and just generally line bundles on P1 being indexed by the integers. This is kind of well, depending on the conventions, this is either that same indexing or it's related by minus sign. So yeah, actually, I'm pretty sure. I'm always confused by these minus signs, but I think in this setup, Ln will correspond to the sheaf O minus n. Yeah. So yeah, you can also say things in terms of divisors and so forth. But anyway, so we have this for every integer we have a sheaf. We have a one-dimensional line bundle on P1. And you can show that it doesn't have any global sections if n is positive, but if n is negative, then we have global sections, and those global sections will be the polynomials of degree minus n. So again, there's this stuff with plus or minus n, but I believe that this is what happens, that I got the signs right. But in any case, we do get homogeneous polynomials in two variables appearing as the global sections. So, and those give you all the representations of both the Lie algebra SL2 and the group SL2. So I will have some discussion of this in the final exam, but I will set everything up for you, so you don't really need to know anything about line bundles beforehand. I hope I'll make it clear enough so that you can understand the problems without needing extra algebraic geometry. Okay, so so that's this special case of Borel-Bott that I was a bit. I just wanted to give a vague statement of it. Let me mention something about the more general statement. So the full Borel-Bott theorem is a description not only of the global sections, but of the higher cohomologies of these line bundles. And it's a description of these cohomology groups as irreducible representations and explicit computations for their central characters in terms of the length function on the Val group and this the shifted Val group action on the characters and dominant weights and so on. Okay, and so that's a generalization in one direction. A generalization in another direction is called Beilinson-Bernstein localization. And this gives us a description not only of the irreducible modules for the irreducible representations for the group or the Lie algebra, but all of the representations in terms of certain sheaves on the flag variety. So we can't restrict ourselves just to line bundles. We need to think about more general sheaves. And yeah, so really it's D modules, so D modules on the flag variety. So let me give you a kind of a cartoon version of Beilinson-Bernstein localization. So what happens is there's this localization functor from representations of the Lie algebra. I realize I'm moving back and forth between mod and rep, but It's okay, it's the same thing. So representations of the Lie algebra, you can take any of them and define a certain sheaf on the flag variety. And in some sense, it's similar to this induction construction, but there's some well, actually no, it's scratch that. It's not really similar. It's a different procedure. And yeah, and so inside the modules for the for the Lie algebra, so modules for the Lie algebra are the same as modules for the universal enveloping algebra, and inside those modules we have those that have a central character, a fixed central character lambda. So all the modules with the same central character. So there's only one irreducible object in that subcategory, but there's various other non-irreducible representations that have the same central character. And those localize, those go under this functor to D modules on G mod B that are twisted by this line bundle lambda. I'm realizing here maybe I think it's actually a different lambda, but you can describe the relationship between these two lambdas. Yeah, so you can, this kind of algebraic category becomes a geometric category of D modules on G mod B. So maybe some of you are in Dima's course on D modules. This is one application. I don't know if you guys talked about this, but this is one application of D modules to representation theory in terms of understanding which sheaves occur on G mod B when we localize representations of the Lie algebra with a fixed central character. And so the Valence and Bernstein theorem describes, so it gives conditions on lambda for when this functor is an equivalence of categories. So sometimes it's an equivalence of abelian categories, other times it's an equivalence of derived categories. Okay, so that was a lot of information, but it's kind of in my mind, it's kind of the next progression in these sorts of ideas that we've discussed in the class. Okay, any questions about line bundles on the flag variety, Borel, Bot, Valence and Bernstein? Okay, so in that case, let me kind of summarize some of the things that we've done today and done in the course. So, so we started out by talking about linear algebraic groups, what a linear algebraic group is, the embedding theorem, Jordan decomposition, various properties of the linear algebraic group. We also talked about certain cases like the commutative algebraic groups, and every one-dimensional algebraic group being commutative, and then tori and diagonalizable groups. And then I guess in the kind of the second half of the course, we attached various objects to a connected linear algebraic group. So we started with defining what the Lie algebra of a linear algebraic group is. And so that was connected to derivations and differentials, and it's connected to non-commutative algebra via the universal enveloping algebra. We also defined the flag variety, G mod B, and that was related to projective geometry. So this is the projective variety. It's kind of the biggest projective variety that appears as a quotient of G. It's also related to moduli spaces. We saw that the flag variety parametrizes the flags. So for GLN, there's this moduli description of the flag variety as parametrizing the flags. It also parametrizes the Borel subgroups of G. And there was the sort of partial flag varieties where we take G mod a parabolic. and projective space p to the n appears as a partial flag variety for GLN. Yeah, and then in the towards the end we define the vowel group, and in particular its reflection representation and the connection to root systems and root data and so on. So I only really defined the vowel group for reductive groups, but I mentioned that there's this general definition: normalizer of a torus among the centralizer. So those are kind of connections to various different topics in mathematics. And yeah, I guess I said that. And then when G is semi-simple, there are kind of strong interactions between these objects that we had. And these interactions are reflected in the connections between the representation theory, and they give us a better way to understand the representation theory of G. As I said today, so the Lie algebra is related to this vowel group action of the reflection representation through the Chevalley restriction theorem. So the center of the universal enveloping algebra is functions on the quotient space. And the Borel-Weber theorem is connecting, in some sense, the line bundles on the flag variety, equivariant line bundles on the flag variety, with this action, this vowel group action. It's actually a shifted action, but it tells you which representations appear, or it tells you the central characters of representations that appear as global sections of equivariant line bundles on the flag variety. And finally, there was the Beilinson-Bernstein localization theorem that lets us take a module for the Lie algebra and define a D module on the flag variety, and this gives us certain equivalences of categories. And yeah, I guess, and also we have the Tanaka reconstruction theorem that characterizes groups that appear as representations of algebraic group, that characterizes categories that appear as representations of an algebraic group and allows us to recover that algebraic group. And an application of that is to see that that the representations of a group are a subcategory. There's a fully faithful functor to representations of Lie algebra. And yeah, I mentioned these other things. Yeah, so I guess that's the course. I'll be in touch about the final exam. So the idea is to I'll probably assign I'll send the questions at some point next week, and then I'll give you about 2 weeks or so to work on the problems, and then they'll be due, and then there'll be very short oral exams or just check-ins. I'll probably just ask you to walk me through a solution to a final exam problem or a homework problem that you've submitted. Yeah, so the oral component is not meant to be a big deal. Yeah, I'll send an email about that. Yeah, are there any questions about this last stuff that I talked about? Okay, well, if there are no questions, then we can call it a day. And yeah, feel free to email me any questions, and I'll email you the final exam questions. Thanks, everybody.
Thank you.
Thank you.
Thank you.